Hello everyone, my name is Ben Poole, and today I'm going to present our recent work on error-related potential variability, exploring the effects on classification and transferability. So the motivation of this work is largely kind of tied to the classical calibration issue with BCI applications, with a specific focus on error-related potentials here. And so in a classical kind of BCI pipeline, say we want to detect the errors for when a robot is going to place an object in the wrong bin. And so whenever these errors are about to occur, this is when we expect the error-related potentials to occur as well within the brain. So typically we'd have to collect some initial data for our training of the model. And then once we've trained kind of this model, we then want to transfer this model to then be performed on the actual task itself. So in this case, we have this source task, which represents our training data. And we have this target task, which really represents our testing data. In this case, both of the tasks are the same. We're using the same task to train and then kind of test on. However, one issue with doing this is that if you have a really complicated target task, or just a very expensive target task to collect data with, it's not really a good idea or desirable to then spend all this time collecting source data for the initial training of our kind of model or classifier here. So one thing we can do is we can replace this source task with a much simpler task that's still eliciting error-related potentials and is much more controlled. And we can elicit much more data with this kind of very simple replacement, whatever that may be. And then we can train our model on this task and then transfer it to the target task. Now, one issue with this is often that when we do this model transfer with transfer learning and whatnot, there tends to be a performance drop. Now, that performance drop can vary, but one thing we'd like to do is how can we kind of overcome this performance drop? And typically in normal machine learning, we look at this at the algorithm level or the model level. How can we make better algorithms for transfer learning? However, there's an alternate perspective, and that's kind of looking at transfer learning from the data perspective. And this is basically just saying, given some source task or some specific source task design, how can we elicit a minimal drop in classification transfer to the target task? However, one main issue with error-related potentials, really brain signals in general, is their variability. Or specifically to error-related potentials, there's kind of these different named variations of error-related potentials, and we're going to kind of see how this will play into our problem after we kind of look at some of these different named variations. One of the first named variations that's kind of important to our work here is the interaction error-related potential, and this is just when basically elicited when an action into an interface is erroneous. So we input some action, and the interface, executes some action that we didn't input. Another kind of famous error-related potential variation here is observation, and this is just a error-related potential that's elicited when we observe an erroneous action. So very general here. And then there are some more, some other notable ones like outcome and execution. Outcome is elicited when the goal of an action is not achieved. Execution is essentially just the continuous version of interaction. So when interface is continuously outputting the wrong action or the action we didn't input. And then there are a few more out there, ones like feedback or related potential or whatnot, that are not listed here, but not incredibly relevant at the current moment. So given these kind of ErrP variations, prior research has really begun to look at kind of some general factors that might give rise to these kind of variations. Two such factors we'll look at today is just awareness and embodiment. And so awareness is really tied to the conscious awareness of a perceived error. And given this kind of black line here, which represents just a cartoon drawing of an error-related potential, when we have higher awareness, we can see in the red drawing that it tends to augment this PD peak by making it larger or having a larger amplitude. Whereas lower awareness, or kind of less aware of the kind of perceived error, or you can kind of be less conscious of the perceived error, the lower this peak will get, or it'll be unaffected, essentially. Additionally, we can look at this other kind of factor of embodiment, and this revolves around the perceived perspective of an error. You can kind of think about this as the self-embodiment of error. How much does that person embody the error that they're observing or committing? And so this kind of self-embodiment of the error tends to augment the ERN peak, so this kind of negative peak here, where you can roughly think about as first person is high embodiment, so it'll create a larger ERN peak or trough here. And we can see that third person tends to not augment the ERN or make it smaller, essentially. Kind of given these two factors that influence ErrP variations, we really want to separate our ErrP variations into two categories. And so the first category here is going to be observational. And this is just any ErrP variation that's elicited while observing a task. And so for example, this largely just includes observation ErrP variations. And the hypothesis here is that these observational ErrPs will be less distinct due to their lower levels of embodiment and potentially lower levels of awareness. And you can see this illustrated here on this kind of right-hand side. And the second category that we're going to be using is interactive. And this is just any ErrP variation that's elicited while interacting with a task. So this encompasses much kind of wider variety of ErrP variations. For instance, things like outcome, interaction, execution, ErrPs are kind of all included under this umbrella. And we further hypothesize that these kind of interactive, or this interactive category here, will produce more distinct ErrPs due to their higher levels of embodiment and potentially higher levels of awareness. So kind of given this initial setup, we really have three main questions that we want to start investigating for our kind of inquiry into this data perspective for transfer learning. And that kind of first question, research question that we really have is, do more distinct ErrP variations produce easier classification problems? Next, we kind of really want to look at what role do these kind of category of ErrP variations play? And also what role does the task similarity play in the task transfer performance? So for instance, what would happen when we transfer using the same ErrP category, but elicited from different tasks? Additionally, we want to look at what would happen when we transfer using different ErrP categories elicited from the same task. These are all kind of just initial questions we want to start exploring. And then finally, from these initial explorations, what are some of the practical implications we can start to kind of extract? So to explore these kind of three different research questions, we come up with two different tasks to collect data from. The goal of these two different tasks is roughly to have two different subtasks for each of these tasks, which will correspond to the two different ErrP categories we mentioned earlier, the interactive and observational. The first task is the binary goal search task. It's the classical kind of task used throughout kind of literature. And the goal of this task is just simply for the blue square to make it to the green square. And the green square will spawn on either side of the blue square, the player object here. And the green square will represent kind of the goal square, essentially. You can kind of think about it as. Now, there's two different kind of subtasks, as mentioned previously. There's an interactive and observational. Here we refer to the interactive as BGS hint. This is where the subject will interact and actually perform the task by pressing keys on the keyboard to move the player object. And then the observational is referred to as the BGS OBS task. This is where a human or subject will watch an agent play the task. And in both of these tasks, there's about a 20% error rate for the object to move in the opposite direction away from the goal, which is when the ErrP is thought to be elicited. Second task is the obstacle avoidance task, otherwise referred to as OA. Once again, it has two different categories, interactive and observational. The goal of this task is much akin to kind of Flappy Bird, where the player controls this blue object, and the goal is for the player to avoid these black obstacles where a collision is considered an error and an ErrP should be elicited. So for the interactive task, we refer to this as OA out, and this is where the subject interacts with the task. And then the observational is referred to as OA OBS, and this is where the subject simply watches another agent to kind of perform the task. So in addition to our kind of two tasks, this is roughly kind of a quick summary of our methodology here. I do just want to briefly point out that the EEG equipment we're using is the ganglion board from OpenBCI. All our channels can be seen on the top right there, and we're kind of focused around the anterior cingulate cortex, as that's where ErrPs are thought to be kind of elicited from. We have a total of 9 subjects. There's 10 trials per each subject. And we have 4 different four different tasks or subtasks, so roughly 40 trials for each subject. And then furthermore, we're using to kind of analyze this transfer performance and baseline performance. We're using to start off EEGNet and sport vector machines. EEGNet is just a popular kind of deep learning network that's been shown to perform relatively decently on error-related potentials or ErrPs. Furthermore, we'll be largely focused on balanced accuracy, as these are usually largely highly imbalanced data sets. Furthermore, our kind of analysis will be highly focused on kind of effect sizes and significance levels. So I just want to quickly kind of go through some of the initial results from our paper and kind of summarize them here. And so for the first research question that's interested in, do distinct signals or ErrP signals produce easier classification problems? We can start by analyzing that by looking at the baselines. So this is when we have the same source and same target task. So you can think about this as BGS int to BGS int is a baseline. We're using the same source and target data. So when we look at the baselines, what we find here is we find that the interactive tasks actually perform the best, as we can see by our ranking here, which is largely determined by the effect sizes measured from a multi-comparison test by comparing all these kind of classification scores. And these are the grand kind of average classification scores across all subjects that are reported here in this bar graph. And so what we see here is the interactive tasks perform the best, and kind of we can extract this kind of ranking where OA out performs kind of largely by far the best for both classifiers, and then followed by BGS int. And then we can see that for both classifiers as well, the observational tasks tie for last place, essentially, as they find non-significant kind of differences between these two scores. And so these kind of, just to briefly touch on, as we'll be seeing these graphs more and more, these kind of bars here represent the multi-comparison test, and then this first number here represents the effect size for EEGNet, followed by the confidence interval, and then this is the effect size for SVMs, followed by its confidence intervals. And so kind of given this ranking, we want to see, okay, we can see the easiest classification problems here pretty clearly. Well, now we kind of want to compare these to the grand signal averages to see if can we associate some sort of distinct signal with a higher or easier classification problem. And when we do this, it's very kind of muddled, as our grand averages are very kind of noisy here, but we do see larger peaks, PE peaks, for the interactive tasks, which kind of indicates this higher awareness potentially. But we don't really see anything reflected per se in the error in troughs, as a lot of the data is extremely noisy. There's much further investigation linking the distinctiveness to the easier classification performance, but at the very least, we can see that these interactive tasks are performing the best as baselines. Looking at the next results for research question 2, this is looking at transfer performance. In particular, these results are looking at within task comparison, so the subtask transfer. And first, we can kind of see here that these results tend to indicate that the observational tasks act as good source data, while the kind of interactive tasks here act as good target data. In particular, we see this with Bach. However, counter to this, for TNR, we see that it is the reverse. Interactive tasks act as the kind of better source data. And then once again, it's returned to kind of normal here, where the TPR, the observational tasks, are acting as the best kind of source data. Furthermore, we'd like to ask the question, based on these kind of initial results, is does observational data serve actually as the best kind of source data, or is it the fact that interactive data serves as a really good target? And by the end of this, we start leaning towards the latter, and we'll kind of see that as we move through more of these results. For the within ErrP category results, this is basically a comparison across tasks with the similar ErrP categories, so interactive to interactive, observational to observational. We first find that for the interactive tasks, it seems that BGSint to OA out seem to perform the best, indicating that BGSint might be some good training data for an interactive task, as we see it's much better than its kind of OA out counterpart. Furthermore, we don't really have any conclusive results regarding the observational side. Here we can see that the EEGNet does indicate some sort of medium effect size. However, the SVM results are non-significant and don't really indicate much of anything. Next, we can kind of see that the OA tasks seem to, once again, produce this kind of higher TNR over the kind of BGS tasks. And additionally, they produce a much significant lower TPR compared to their BGS counterparts. The next results look at what happens when we perform a multi-comparison task when holding the target task the same. So we're only kind of changing the source task and then seeing how they perform on different target or on the same target task. So here we first notice that the baselines tend to perform the best. So that's just BGSint to BGSint, BGSOBS to BGSOBS, all tend to always perform the best, followed by their same task counterpart, not the same ErrP variation. So that means BGSint to BGSOBS tends to perform the second best. And these are all kind of expected results for the most part. There are some exceptions with OAOBS, and it's basically having a tie for second place across all the other different source tasks. However, more interestingly here, we do notice that for each of the target tasks, the TNR is maintained based on the source task. So you can see this TNR ranking does not change even when the target task is changing as well. And we'll see this again in the next results as well. So for the next results, we want to do the same thing, but instead of holding the target task the same, we hold the source task the same. And so when we do this and we do a multi-comparison across the different target tasks for a given source task, what we find is very interesting, and that is that OA out tends to perform the best, or similar to that of the baselines. So here we can say BGS when training on BGSint and testing on BGSint, there's a similar score when training on BGSint and testing on OA out. And we kind of see that no matter what for all back TNR and TPR for the most part. It's either tied with or outperforming. Interesting enough, we can also see that the source task TNR is maintained, as we can see here. For each different source task, all the different target task TNRs are all relatively tied. And so that's another kind of interesting takeaway here. So just as a quick summary of some of the practical implications that we extract from these results, the first being kind of that interactive tasks do seem to produce easier classification problems, while observations seem to produce relatively harder problems. Furthermore, we can see that interactive tasks do serve better as target data, or tend to serve better as target data when performing transfer learning. This is very clear for the OAA task in particular. It seems to be very well acting as the target data and very bad at acting as the training data in some different aspects of transfer. Additionally, we can say that to be expected, similar tasks do seem to be the kind of safest source data when acting as transfer. And then finally, if we were to make a recommendation for is there kind of all-around decent data to use as a source task, that relatively seems to be true for BGSint. It doesn't really suffer from the extreme qualities of OA out and has relatively average performance, and it has that benefit of being a much more controlled environment just in general. And with that, I just want to thank everyone for listening to our presentation. Feel free to contact us. Our emails are listed here. You can also refer to our GitHub link below or the QR code, which links to the GitHub, to check out our code, our results, our plots, and in the new future, we'll be releasing the EG data on the GitHub as well. So thanks again.